So, welcome to our presentation. We're going to talk about trend analysis using Kalman filters today. We're going to use two different process models and show our results we obtained. But before starting, I need to say that we had some changes on our report and we're going to send it to you via email after this video so we can continue. Next page. Thank you. Kalman is the father of Kalman filters, as you know. He started this process, this researches about filtering and estimations and sensor fusion in 1960. And here are other resources, references we used while preparing our project. Next page. This is our system model, the previous state, the prediction step, update step, and the measurement. Here are, as you can see, the main equations about preparing a Kalman filter for our usage. Xk is the state vector. Xk is the state vector at time k. F is the state transition matrix. And Wk is the process noise. And here you can see the observation equation, as Zk is the observation vector, H is the observation matrix, and Vk is the observation noise assumed to follow the values we chose. So our first process model is geometric Brownian motion, GBM. The equation for it is as written here. And ST is the stock price at time t, mu is the drift rate, sigma is the volatility, and WT is the winner process. This is our other process model named ARIMA. It has three coefficients: regressive part, a model that uses the dependency between an observation and a number of lagged observations. The integrated part, differencing the data to make it stationary. The moving average, a model that uses the dependency between an observation and a residual error from a moving average model applied to lagged observations. Here you can see the equation for the ARIMA process model. Yt is the value at time t. Phi represents the AR coefficients. Theta represents the MA coefficients. Et is the error term. We can continue. So before we implement our filter, these are our selected values. The initial stock price is 100, for example. Drift rate is 0.05. Volatility is 0.2. And you can see all of this as written here. The winner process is the cumulative sum of the matrix shown here. And while setting up the Kalman filter, we chose the state transition coefficient as 1, observation coefficient as 1, process noise covariance as 0.01, observation noise covariance as 1, initial state estimate will be S0, and initial estimate covariance will be 1. This is our graphic. We're going to simulate it a little bit later. Yeah, here you can see the GBM simulation. Let's run it. This is our graphic we obtained for GBM. You can change the values of mu and sigma, the drift rate and the volatility, and simulate other graphics. Let's set sigma as 1, for example. You can see how the graphic changes, and etc. Let's continue with ARIMA. We had three variables, let's say, P, D, and Q. P is the AR component, D is the I component, and Q is the MA component. And here is the equation for it. You know that as written here, phi b is the AR polynomial of order p. 1 minus b to the power d is the differencing operator, and theta b is the MI polynomial of order q. ET is the white noise error term, as you can see, as you can read. And this is our ARIMA plot. Let's simulate it. You can see the observed stock price is shown with black dots here. This process model requires, I mean, used for more systems that has more noise. If you have more noise, it will be more accurate for you to use ARIMA as the process model. GBM is used for slightly less systems that has slightly less noise, and ARIMA is for systems that has more noise, you can say. So in conclusion, we can say that Kalman filters are really useful for trend analysis, and you have to choose from two different process models. If you are trying to analyze a more basic structure, you can use GBM as your process model. And if you are working with a more complex one, you can use ARIMA as your process model. So in conclusion, we think that it is a really reliable tool for our investments. And here are our references we used to prepare this project. And thank you for listening to us.